So the kinds of problems for Module 13 for today's lecture are temperature conversions and thermal expansion, and the next big topic is ideal gas law calculations. So temperature is usually measured either using Fahrenheit or Celsius scales. For scientific reasons, it's usually Celsius or Kelvin. So water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. The Celsius scale is designed so there's exactly 100 degrees between boiling and freezing. Whereas in the Fahrenheit scale, water freezes at 32 and boils at 212. So 1 degree Fahrenheit is smaller than 1 degree Celsius. The two conversion factors are shown at the bottom. Temperature in Fahrenheit is 9/5 Tc plus 32. And the temperature in Celsius is 5/9 times the difference between the temperature in Fahrenheit minus 32. So let's do a couple of calculations. So on the moon, the daytime temperature is 127 degrees C. Express this in Fahrenheit. So all I have to do is put in the temperature in C in the equation in the correct spot. So TF is 9/5 times 127. And then when I've done that, I add 32 onto it, and I get 260.6, or 261 degrees F. Pretty straightforward. The nighttime temperature is minus 297.4 degrees F. What's this in degrees C? Well, temperature in degrees C is 5/9 times TF, which is minus 297.4 minus 32. So you have to subtract 32 before you multiply by 5/9. And I get minus 183 degrees C. Okay, so normally, since 1 degree in Celsius is a bigger jump than a degree in Fahrenheit, the numbers you get for Fahrenheit will be bigger than the numbers for Celsius. So when I take two objects that have a different temperature and I put them in contact with each other, eventually heat will go from the hot one to the cold one and they'll become the same temperature, and we call that in thermal equilibrium. So the zeroth law of thermodynamics says that if you have three objects, A, B, and C, and A and B are in thermal equilibrium with each other, and B and C are in thermal equilibrium with each other, then that means that A and C must also be in thermal equilibrium. It might make more sense if you think about it if they have the same temperature. So if A has the same temperature as B and B has the same temperature as C, then A and C must also have the same temperature. And we call this the zeroth law of thermodynamics. So what does it mean when something is hot? Well, as an object heats up, its atoms vibrate faster and push each other further apart. So they vibrate harder and further. So that means that an object that's hotter in general gets larger. And you should remember what happens for a hot object as opposed to a cold object. So if something gets hotter and the atoms move further apart, it's going to get larger, and we call that thermal expansion. So if you have a long straight object, its length will increase, and we call that linear expansion. So as the object heats up, the atoms push each other further apart and the object grows. And that's why we have cracks between sidewalks. And if you see here on the bridge, there's expansion panels so that when it heats up, the bridge doesn't actually get damaged by the thermal expansion. So the change in length is just proportional to the initial length. It's proportional to the change in temperature. And it's also proportional to a coefficient of linear expansion. We use the Greek letter alpha there, which depends on the material. Some materials don't expand very much. Some expand a lot when the temperature changes. And that alpha depends a little bit on temperature, but usually we treat it as though it's temperature independent. So delta T is T final minus T initial. Of course, if an object is three-dimensional, its whole volume will change, its length, its width, and its height. And so for volume expansion, the change in volume, it's essentially the same equation. All I've done is I've replaced the symbol alpha with V. And instead of alpha, we use beta, where beta is the coefficient for volume expansion. And for most uniform solids, it's about 3 times the linear expansion. A bimetallic strip is used to measure temperature and control thermostats. You can see a picture of it there, of brass and steel. Since brass expands more than steel, it has a higher value for alpha. When the temperature increases, the brass expands more, and so the rod will bend down. And as you cool it down, the brass will shrink more, and then the silver part will curl upwards. So the direction of it can change, and if I have an electrical switch in the way, when this thing contacts the switch, it can turn a heater on or turn a heater off. This slide just shows you an example of the thermal expansion coefficients, linear and volume, for a few materials. You can see they're very small numbers, and therefore aluminum, you can see that the beta, the volume coefficient, is exactly 3 times the linear coefficient. So here's a question for you. Does a hole get bigger or smaller when it's heated? So if I take a pipe, like in shown in A, and I heat it up, what will happen? Will the hole get bigger or will the hole get smaller? Well, one way to think about it is think about, what if you had a solid disc like shown in B? If I have a solid disc like shown in B, when I heat it up, I expect all the particles to move out radially, right? So if I imagine this dashed line, if I draw a line on it that's like the edge of the hole in the pipe, you can see that dashed line would actually move out. So the hole will actually get bigger when it's heated. And that's why if you've got a lid on your jelly jar or something that's stuck, and you can't get it off, run it under hot water and the lid will get a little bit bigger and you can take it off of your glass jar. All right, let's do a sample calculation. So a steel beam 10 meters long is installed at 20 degrees C. What's the change in length if you cool it down to minus 30 degrees C, and we're told the coefficient of linear expansion for steel is 12 times 10 to the minus 6 per degree C. All right, so what do we want to do? We're going to do the same thing, gather from the problem. So the beam is 10 meters long, so that's my L. It's installed at 20 degrees C, so that's my starting temperature. Let's call it T initial. We're going to go down to negative 30 degrees C. So that's going to be my T final. And the coefficient of linear expansion for steel is 12 times 10 to the minus 6. So that's my alpha. And it's per degree C. Okay, so what's the equation? I want to find delta L, and my equation is just delta L is alpha L times delta T, which is T final minus T initial. So the problem gave me all of these, so it's just going to be a straight plug and chug. So I've got alpha, 12 times 10 to the minus 6. The length is 10 meters. And then I'm going to do T final, negative 30, minus T initial, which is plus 20. So I get negative 0.006 meters, which is 6 millimeters shorter. Okay, so the negative change in length tells me it got shorter, which is what we expect when it gets colder. It grows when it gets hotter, shrinks when it gets colder, and it only shrinks by a very small amount. But however, this amount can be significant if you've got a building that's continually expanding and contracting. It can damage around the steel rivets, for example. They can get pulled bigger and smaller, and eventually you can get metal fatigue and the building could collapse. So engineers have to take these things into account when they're building buildings. All right, so here's your problem. I just want you to do a similar problem. So we've got a metal rod that changes from 1.721 meters at 100 degrees Kelvin to 1.725 meters long. So it goes up by 4 millimeters in length at a higher temperature. And the thermal expansion coefficient is 6.25 times 10 to the minus 6. So I want you to find what's the final temperature of the rod in Kelvin, and then express this temperature in Celsius and in Fahrenheit. So what's a degree Kelvin? 1 degree Kelvin, a delta T in Kelvin of 1 degree is the same as the step size for Celsius. It's just offset by 273.15 degrees, which is absolute zero. So the Kelvin scale is just a Celsius scale, but it's offset lower down so that 0 degrees Kelvin is the lowest temperature that anything can absolutely get.